Hi guys, I'm going to talk to you about exponential functions. And most of you have had some experience with exponential functions. Most likely, if you have a savings account, you have experienced it as an interest rate or a growth factor that's applied to your money while it's being stored and cared for at the bank. Okay, so exponential functions are part of our packet because since we're planning a future city, we wanted you to have the ability to look at some existing data that we have regarding the city and the county's plan. And so here, I actually have you reading a little bit. So this is less like math and more like language arts. We have you doing a little bit of reading to understand what forecasting population is all about and why it's important and what you have to look at while you're considering it. And we want you to create a model that models that population growth projections and do some forecasting. So as part of that, we're going to teach you a little bit about exponential functions, or possibly review for those of you who've already had some experience with them, and do your best work on this. So the general formula of an exponential function looks like this. Y equals a b to the x, okay? When we can plot this, just like we plot any graph, we can make a data chart, right? And we can do x and y, and we can put in an x value and we can get out a y value. If we put in different values for x, we'll get out different values for y, and then we can plot those points on a graph. Okay, so that's fundamentally no different than anything else we've done. So a is a number, right? And a can be less than 0 or bigger than 0, or can be 0, but if it's 0, what is y? 0, right? B is what we call our factor. So both of these are examples of our factor. It's either a growth factor or a decay factor, okay? You guys see that? So if B is greater than 1, it's a growth factor. So if your money's in the bank, you might be making 3% on your money. That might be the rate they give you. The R value they give you is 3%. So they take the principal you put in, which is 100%, and they add 3% to it. So it would be 103% that you're getting on your money, meaning that your principal is preserved and you're getting another 3% on top of that, okay? So that's your factor. So this one right here represents the principal that you've put in your bank account, okay? Decay is going to have a B value of less than 1. So if I said my B is 1/2, right? Then I know that my factor is a decay factor, and I can calculate my B if I'm given my rate, or I can calculate my rate if I'm given my factor, whether it's growth or decay. Okay. R is your rate. Okay, so R is an element of your factor. It doesn't show up in this equation, but we could insert this 1 plus R in here in parentheses, or we could insert the 1 minus R in parentheses in here. And you're going to see that a little bit as I go through our dynamic classroom and I share that information with you. So if your rate is given to you as a percentage, you're going to want to divide it by 100 to use your decimal of that rate, okay? Because this represents your 100% or your principal or your starting amount, okay? So so that's really important right there, okay? And I'm going to add a little bit more information on this and a few more details as we work through some problems in the dynamic classroom. But this is kind of overarching a core concept, and I'm going to share with you some of that as well. Okay, so we are talking about exponential functions, and I just gave you the overarching general function, what it looks like, and what the different elements of it are. But one of the things we have to do is be able to tell whether or not we're looking at an exponential function from looking at a data set. And so one of the key elements of our exponential function is that it has this factor that everything is being multiplied by as we move through the function. And so if we take a look at our data set here from 0 to 1 to 2 to 3 on x, when we put in that x value, we move from 2 to 4 to 12 to 48. So is there a factor that this is being multiplied by that gets us to 4? Well, you might say, oh, well, 2 times 2 is 4. Okay. So if that's the case, then we multiply this 2 by 2, we get to 4. When we multiply 4 by that very same factor of 2, do we get to 12? We don't. And so that's a problem if we want to say that this is an exponential function. And so as we look at this, we see that as we add 1 to our x value, the first term is multiplied by 2, the second term is multiplied by 3, the third term is multiplied by 4. And so, oh, it's not clicking for me. Interesting. As x increases by 1, y is not multiplied by a constant factor, so it's not exponential. If it were exponential, what we would see from this first term multiplied by 2, we should see 8 here, and then we should see 16. And that would tell us that it's exponential. It's multiplied by the same factor. So let's take a look at this example B. And as we can see, we move from, as we add 1 to our x, we move from 4 to 8 to 16 to 32. Well, I know that 2 times 4 is 8. Does that work? Do I move from 8 to 16 by multiplying by 2? And yes, that absolutely does work. And do I move to 32 from 16 by multiplying by 2? And yes, that absolutely does work. And so I'm trying to make it show up here for us. It's being a little bit ornery. There we go. That yes, as we add 1, we multiply by 2. And it does tell us, again, as x increases by 1, y is multiplied by 2. So the function is exponential. Okay? Okay, so I want to talk just briefly about graphing these exponential functions, how we go about graphing them, and to remind you about how to determine what the domain and range of a function is. So the domain of a function is always the possible x values that the function can have, and the range is going to be the possible y values or outputs that the function can have. And what you need to remember is that we can always put in an x and get out a y. We can always set up our data table, x in one column, y in another. We can always put in a value for x and find out what our y is at that particular value and graph those points. So this is exactly what they suggest you do with this problem. You put in values for x and you get out a y. So they've chosen a -2, a -1, and then 0, 1, and 2, and these are the output values that they get for those. Okay? The second step is to plot those pairs. So as you can see, we have x of -2 right here, and y is 1. We have x is -1, y is 2. We have x is 0, y is 4. So for those of you that are in integrated 1, that's the y-intercept that we've been looking at with linear equations. But here with our exponential function, we also have a y-intercept. So if you're asked for the y-intercept, you would be putting in a 0 for your x value. So remember, any number to the exponent of 0 is going to be 1. And 1 times 4 is 4. So when you put a 0 in for x, you get out a 4. Okay? Step 3, this particular problem asks for you to compare the graph to the graph of the parent function. Okay? And so the parent function is 2 to the x. It's without this 4 in front of it, okay? This 4 changes the function. And as you can see, that 4 in the front of it makes this steeper, okay? It makes it make it turn more quickly and go up higher faster, okay? So the parent function is g of x equals 2 to the x. The graph of f is a vertical stretch by a factor of 4 of the graph of g. So the vertical stretch means it makes it go up faster. It becomes more vertical. It stretches, for example, this point would have been closer to the x-axis. So it stretches that out and makes it farther away, okay? The y-intercept of the graph of 4. Okay guys, I just wanted to come back to this idea one more time. This core concept is in your packet. This core concept is found in your book. It should be very helpful for you as you work through these problems. Exponential growth occurs when a quantity increases by the same factor over equal intervals of time. And so we saw that with our table of data, and that's how we could tell that, that we had an exponential function. So exponential growth functions is a function of the form y equals a times 1 plus r to the t. So we saw that earlier on my board as y equals a times b to the x. So now our variable x is a t, and our b has this 1 plus r inserted in for it. And on my board earlier I said that b is your factor, okay? And it can either be 1 plus r, which makes it a growth factor, or it could be 1 minus r, which makes it a decay factor, okay? So a couple of other important things looking at this diagram here. This diagram is very helpful. So y is your output, or your f of x, or f of t, sorry, in this situation, f of t, because t is what changes. So it's your final amount. A is your initial amount, okay? If you put $500 into your savings account, A is your initial amount, okay? That's really important. And then your B value is this whole thing right here, the 1 plus R. And R is your rate of growth. It's in decimal form. So if you're given the rate of growth in percentage, you have to divide by 100 to get your rate of growth in decimal form and use it as part of your B value. This is a growth factor because it's 1 plus R. So your B value is a growth factor, okay? So here is this idea of exponential decay. This is also in your packet, I believe, and it's also in your book. So you should know where to find it in both places. Notice over here the study tip. Notice that, and this is what I was talking about in the last little segment about exponential growth. Notice that an exponential decay function is of the form y equals a times b to the x, where b is replaced by 1 minus r because it's decay, and it's losing value instead of gaining value, and x is replaced by t because we're talking about what happens to something over time. Okay, so a is still your initial amount, your starting balance or your starting principal. You started with $500 and maybe instead of gaining money you lost money, so your rate of decay again is in decimal form. So if you're given the information saying you lost 10% per year on your balance, you have to think of that as a decimal. So you have to take that 10% and you have to divide it by 100 to get your decimal. This is a decay factor because it's 1 minus r. Okay, so let's take a look at this example. It says the inaugural attendance of an annual music festival is 150,000 people. The attendance y increases by 8% each year. Write an exponential growth function that represents the attendance after t years. So we want to start with our initial value, which is going to be 150,000, And we want to think about our rate, which they give us to in percentage, 8%, but we have to divide that by 100. So once we do that, our rate is going to be 0.08. And so our exponential function is going to be y equals 150,000 times our b value, where our b value is a growth value because it increases, right? So it's going to be 1 plus that point, that 0.08. This will be 1.08. 150,000 times the quantity of 1.08 to the t power. That's what I would say. The initial amount is 150,000 and the rate of growth is 8%, or 0.08. So we have to write this growth function down, and that was on the previous slides that we looked at, right? We put in our initial value, A, which is 150,000, and our rate, which is 0.08. So these are important things to write down. Write down A equals 150,000, write down R equals 0.08, then you have your equation, and you can fill in what was missing, okay? And then they tell you how many people will attend the festival in the 5th year. So when t equals 5 is what you're looking for, and you want to round your answer to the nearest thousand. The festival attendance can be represented by y equals 150,000 times 1.08 to the t. That's what we have right here. And you put in, t equals 4 represents the 5th year because the 1st year is 0. Sorry, that's my bad. So instead of 5, you would put in 4 because the 1st year is when t equals 0, right? So that's my bad. Sorry about that. Okay. And we come up with, we put in 4 for t, and we come up with 204,000.0.